In this podcast, we are going to cover a very specific part of carbohydrates that we covered in lecture, and that is identifying alpha and beta anomers of carbohydrates, as well as identifying alpha and beta and then numbering glycosidic linkages. Okay, in both of these examples, we are working with D-glucose. So that is the glucose that's found in nature, and we determine that from our Fisher projection. All right, so we're going to start with D-glucose, and we're going to start by numbering the chain. When you have a cyclic hemiacetal, like we have right here, this is our carbon with an OH on it, and our carbon connected to an ether. That's what makes it a cyclic hemiacetal, which is more stable than the acyclic. We need to start by looking at that oxygen. That oxygen always needs to be in the upper right-hand corner with the tail, I call this guy the tail, pointing upwards. That's how we orient ourselves with carbohydrates. So notice on this side, again, you have that oxygen in the upper right-hand corner and your tail is pointing up. So once you've oriented yourself, you can start to number your carbons that are in the ring, and we can figure out if this is the alpha anomeric form of glucose or the beta form. So I'm going to go ahead and start with my oxygen right here, and I'm going to move clockwise or down to the right. This is carbon number 1 from my Fisher projection, and going around the ring, 2, 3, 4, 5, and this was the bottom of my Fisher projection at carbon number 6. Okay, this was 5 was my last chiral carbon. That chiral carbon was involved in the formation of that ether with carbon number 1, which was the carbonyl. Okay, so now that this is numbered, I know that my anomeric carbon is always on carbon number 1. Carbon number 1, we are going to look and see, is my OH above the plane or below the plane. So looking at both of these pictures, you can have OH in either position. My Fisher projection doesn't show me this. So I see, and I'm talking about the plane of the ring, as it's drawn here, you would look, is it pointing up or is it pointing down? In this case, it's pointing up. Because it's pointing up, this is the beta D-glucose. Okay, beta is telling us that that OH is in the up position. Looking at our other glucose molecule, I'm going to orient myself. There's my oxygen going down to the right. 1, 2, 3, 4, 5, and 6. I look at carbon number 1 to tell me if this is the alpha form or the beta form, because that is variable. That changes depending upon how the acyclic hemiacetal folds on itself. So we have the oxygen, the hydroxyl group, pointing down or below the plane. So this is the alpha form. So here we have alpha D-glucose. Okay. One way to remember this that I like is beta is above where birds fly. Okay, beta, birds, both are bees. That helps me remember it. And then alpha looks like a fish. Okay, and fish are down in the sea. Okay, and another way to kind of think about that alpha is just, it kind of points down anyway, if you think about it like that. And that's how I can keep those two straight. But you always have to look at that anomeric carbon. That's the carbon you want to find in order to figure out, am I dealing with an alpha or a beta anomer? So here we have D-fructose, and fructose is a little different because fructose is not an aldohexose. It doesn't have an aldehyde or a carbonyl at the top position. It's an ketohexose. So it has a carbonyl on position number 2 on the Fisher projection. So because of that, we wind up with a tail on 2 different locations. So let's start by orienting ourselves. In a ketose, usually our ring has 4 carbons in it. For the examples we're going to do, they have 4 carbons in it, so 1 less carbon than the previous. So we put that oxygen at the top of the ring with our tails pointing up. And now let's start to number our chain. Always start to the right of your oxygen that's in the ring. Okay, but be careful. This is carbon number 1 up here, and this is carbon number 2. 3, 4, 5, and 6. So this is also a hexose, but because of that ketose, or that carbonyl at carbon number 2, it folds a little differently. So in the case of ketohexoses, carbon number 2 is our anomeric carbon. That's the carbon we look at to figure out if we're dealing with the alpha form or the beta form. So same rules apply. I'm looking for that OH group that's on my anomeric carbon. In this case, it's pointing down rather than pointing up. My tail is up and my OH is down. Because this is down, this is the alpha form of D-fructose. Looking at our other example, I'm going to start by numbering. Here's my oxygen, and I'm going to go to the right. 1, always start with the tail. 2, 3, 4, 5, and 6. So carbon number 2 is the one that's involved. That's our anomeric carbon, and I'm going to look and see, is the OH pointing up or is it pointing down? And in this case, it is pointing up, or it is above the plane of the ring. Because it is up, it is the beta form of D-fructose. So let's talk about what happens when you join two glucose molecules. Both of these are D-glucose. And our anomeric carbon, I'm just going to number this chain to show you. On the first glucose molecule is going to determine what our glycosidic bond looks like between the two monosaccharides to form a disaccharide. So here I see that I'm dealing with alpha D-glucose because my OH group on the anomeric carbon is pointing down. So there's going to be an interaction between both of these OH groups. And what's going to happen is I will remove a molecule of water. So I'm going to remove a hydrogen from one, and I'm going to remove the entire OH from the other. And what will be left is just a single oxygen, which is where they're going to be joined. So let's look at this when they are joined together. Okay, so now we have two glucose molecules together, so we consider this disaccharide to be maltose. Okay. And notice that when I remove a molecule of water, or it goes through a dehydration reaction, the removal of water, we form a bond right here. And this is called a glycosidic linkage. And glycosidic linkages, just like your anomeric carbons, can be above the plane of the ring or below the plane of the ring. So we can describe them as being either alpha or beta glycosidic linkage. So in this case, since we are pointing down, we call this an alpha glycosidic linkage. And the other thing your glycosidic linkage needs is it needs a reference to what carbons are involved in the chain, because that's going to affect the structure. So counting from our oxygen, going down to the right, 1, 2, I'm not even going to finish counting this because carbon 1 is involved. And I'm going to count this one going to the right from the ring, 1, 2, 3, 4, 5. I'm not going to finish because I can see here that carbon number 1 and carbon number 4 are involved in making this glycosidic linkage. So I would call this an alpha 1, 4 glycosidic linkage. And that is going to refer to the fact that my bond, my glycosidic bond, is going down or below the plane. Okay, if it were pointing up, we'd call it a beta. And the 1, 4 refers to the fact that it's carbon number 1 and carbon number 4 involved in that bond. I'm not done describing this. I've just described the bond. Maltose can also be alpha or beta. And the place we look to determine if it's alpha or beta is to the free or the open anomeric carbon. So looking at this anomeric carbon, it is not open. It does not have an OH on it. It's involved in the bond, so I can't use that one. Let's move to our next anomeric carbon. Looking at this anomeric carbon, I notice that my OH on the open anomeric carbon is pointing up. So this would be beta, and this is D-maltose. I would refer to this as the beta D maltose. Now, that OH group could also be in this position, in which case we'd call it alpha D maltose. So keep in mind that in your name, you're referring to the open anomeric carbon, but in your linkage, you're only looking at how are these two monosaccharides joined together. So let's look at how this bond is different if we are dealing with, we still have both glucose molecules, but in this case, we have a beta glucose molecule being joined to a beta glucose molecule. Okay, so notice that our OH is pointed up at this time. So these two OHs are going to be involved in a dehydration reaction. So we're going to remove a molecule of water. But because my OH group is pointed up, I'm going to get a different type of bond. Also notice that typically when we write these, you're going to have one that's higher up, one monosaccharide that's higher than the other, because when we form that bond between those two, it's going to be in an upward direction. So, okay, we're taking out an OH from one side and an H from the other to form our glycosidic bond. So here's our glycosidic bond. Let's start looking at our product here. In this case, we're going to count again to make sure that we can correctly describe the glycosidic linkage. So I'm only going to count until I've described the carbons that are involved. So now that we've counted, I notice that the carbons involved in my glycosidic linkage are carbons 1 and 4 again. But this time, my linkage is above the plane. It's not pointing up, it's not pointing down this time, it's pointing up. Because this is pointing up, I would call this a beta glycosidic linkage, and I'm going to also mention what carbons are involved. So I have a beta 1,4 glycosidic linkage. Okay, what that does is it's describing just the linkage. It is not describing anything other than the linkage. So I have just described this. Now I need to go back and think, okay, I have a glucose monosaccharide plus a glucose monosaccharide. That means my disaccharide is called maltose. In order to classify maltose as an entire molecule as being either alpha or beta, I need to look at the first open anomeric carbon. This anomeric carbon, carbon number 1, is not open. I don't have an OH group on it, so I can't use it. This anomeric carbon is open and does have an OH group on it. So I'm going to look at this anomeric carbon on the end of the disaccharide, and it is above the plane of the ring. So I would call this beta D maltose. If the beta were, or if the OH was below, we'd call it alpha. But in this case, it is not an alpha because the OH is above the plane.